Test test. Hello, my name is Glenville Pecor, and before we get to Newton's second law, let's basically um let's describe the things that we need to know. Everything that we need to know. Well, one, what's a force? Well, force is here's a good example of force. I quickly wrote this up because I thought it'd be a good example. Force is a thing that an elastic band exerts and stretch. Or when a guy pushes his feet on the pedal, he exerts a force on the pedals. Or when the wind exerts on the side of a building. Most well-known force is gravity, because gravity is there no matter where you are. You could be the farthest possible distance away from Earth in the observable universe, and there's still gravity. It may be very, very little and irrelevant, but it's still there. There's no such thing as zero gravity, and that means there's always a force acting upon someone. Well, let's say you have tug-of-war with a car. Here's another example. The force is present in the strap between the two trucks of the rope, but there also is the force on the rope on the car and the force of car on the rope. We'll get into it a little more later. So now let's go to mass. Mass. All objects have mass, no matter what. Like a brick. There's an example of mass. A few objects, a hammer for example, rely on their mass to function. Like when you're hitting a hammer, it's using its mass with the force due to your hand pushing down the hammer, and gravity uses its mass to the nail. So basically, mass never changes. The mass of an object is always the same, no matter where you go. Every object has mass. Now let's go to the last and most important thing: acceleration. Acceleration is the way of measuring a constant increase in velocity. Or it doesn't have to be constant in some cases, but most cases that we're doing right now, they are constant. So, if an object is accelerating, then moving faster and faster. If an object has zero acceleration, it may be stopped, or it is moving at a constant speed. Basically, let's say here, I'll just say a better example. What I wrote was not the best here. Let's say acceleration, the most common one. Oh, gravity. We proved in one of the Newton's videos I made earlier was that the gravity is always pushing down at 9, about 10 meters per second. Squared. Don't forget, squared. Meters per second squared. So acceleration is basically, it's the slope, in math terms, it's the slope of the velocity graph. And in non-math terms, acceleration is the meters you move in seconds squared. Well, let's go into what mainly Newton said. Now we're going to do a quick lab. Basically, this is what the procedure we did was. Well, this is the procedure that we did. We assembled a ramp. We set the cart to the top. You basically you put the car on top of the ramp. You put a force like sensor on the bottom of the ramp. When you release the car, it finds acceleration basically. And what you did was repeat over and over again and change the slope. So basically, variables that we have here are total force, or net force, acceleration, and mass, which we keep constant no matter what. So once we did the lab, you got y equals mx plus b. Oh, how common. But the slope was 0.5. So we got total force, which is in y. The force in newtons, which is the y graph, is equal to mx with slope, which is 0.5 newtons over meters per second squared, times b, which is the acceleration. So what do we get from that? So we get from that can prove that. Oh, and also, by the way, if you do newtons divided by meter per second squared times acceleration, basically that equals newtons times meter per second squared over meter per second squared, which equals newtons. So if you do that, it gets up to the total force. So what are we saying? We're saying that total force has to equal mass times acceleration. Wow, that's a really cool thing we learned. So let's put this to example in real life. You're pushing with a force of 100 newtons, and you have a mass of 20 kilograms. friction is also a force of 40 newtons. So what we're saying is that you're pushing, there's going to be a force. There's going to be a force of you. Here's a picture of the object we're doing. This is you. This is the box. You are pushing this box this way, but there's some less stuff in it. While you're pushing it, you will be pushing with a force of how many newtons does it say again? 100 newtons. So let's quickly draw a force diagram. So let's quickly draw the stuff that everyone knows. Boom, gravity. That has to be there. Normal force, because there is a normal force because it's touching the ground. This box is the ground right here. Right there's the ground. So normal force and gravity, they're both equal to each other because there's no force that's pushing it diagonally. There's only a force pushing it horizontally. Sorry, I don't know why this moved. Now you have a different force. You have two more forces that different. Well, there's one that we really never talk about. It's friction. But let's go to we'll save that best for last. We're going to be pushing with a force of 100. That's a lot. So, and also but there's friction of 40. So right here, there's a force of 100, 40 this way, 200 newtons up, 200 newtons down. Gravity, these are equal to each other, so this is cancels out. So let's put them all together. There's going to be, let's find the total force. So let's just put these together. This plus this plus this plus, wait, this isn't small enough. What are we missing? Oh, we were missing total force. Let's insert the total force right here. Remember, with total force, it's different. So basically, it's tail to head here. This is the total force. So how do we figure that out? Well, it's simple. These two are both 200 newtons right here. Why? Because gravity. This is gravity. This is weight due to Earth on the box, pushing it down. So this is equal to normal force, which is the floor on the box. So since those are equal, these two are the same. This, since it's a square, since it's a rectangle, there's right angles everywhere. So this means this angle right here has to equal this. This line here has to equal this line. So we know this line due to friction, like I said in the problem, is 40 newtons. And we know this one is 100. So 100 minus 40 equals what? So this means total force is equal to 60 newtons equals total force. With that in mind, so now you know total force is 60 newtons. How much? Now let's do the part of the equation what we learned from the graph. So test. So sorry, my headphones, they died on me, so it may sound weird picking up from here. So we have 60 total force. So from that we also knew that 20 kg equals the mass. So we know that total force equals mass and acceleration. And if you have newtons over kilograms, because we're trying to isolate acceleration, this is what we would get. 3 meters per second squared equals acceleration. So with that in mind, we have that. Test. Okay, sorry, coming back again. So now what's a common misconception? Well, people think, remember there's friction in this problem right here, the friction. Where people think, let's solve the problem, but we're going to put a new factor in. Let's say I put a 100 kilogram box. No, not drawn to size, but 100 kilogram. I'll just take a 10 kg and make it look nicer. 10 kg, you're pushing it. So will this be bigger? Well, no, actually, because this line won't be bigger, but the different line would be bigger. You'd have a different total force. You'll have everything's different, but friction. Everything besides, in this problem now, because you add more weight, everything besides the friction line will stay the same. Most people think, oh, more weight. Oh, what does that mean? That means the friction is going to be greater. But that is where they're wrong. Only thing that does not change is actually the friction, which is very interesting. So now the problem is 60. Total force is 60 now. You're pushing with total 60. Okay. Yes, total force is 60. Now, let's say if you're pushing with 60 still. If you're still pushing with 60, but the weight got bigger. So the only thing that changed is that basically, oh, this got bigger, so you move this down. And this also got bigger. But why didn't this change? Well, because weight does not affect friction. Only thing that affects friction is the surface on it. So let's say this is carpet on carpet. If you put more weight on it, the friction won't change, the surface isn't changing. But if you flip this box, pretend there's wood on the top and on here. Let's say you flipped it. Boop. Well, by the way, ignore this right now because since you changed the mass, the acceleration is wrong. So this is wrong. Let's quickly just do this. So by the way, this is the wood size down. Let's just quickly fix this. Okay, so I didn't want to show you the work because I already showed you the work problem, so you probably know. But now, since this has changed right here, the surface, this gets smaller because this got bigger. And how do we tell? Well, this is smaller. Oh, the total force would be different because you're pushing with the same amount of force, but there's more friction. Let's say the friction went up 20 more. So the friction, instead of being 40, is now 60. So what's 100 minus 60? Well, that's 40. So now total force is 40. Mass is still 30. So what's 35? So the acceleration is 4/3 meter per second squared. Sorry, that was my mistake. So I quickly fixed it. Only thing that's what happened when you switch surface. And how is this true? Well, I'll show you how it's true. And I will tell you why in the next video because I'm running out of time. So, part of Newton's second law, I will explain friction with this. So, hopefully you can see the next one. I'll see you in a couple of seconds.